Welcome back to another video lecture, and today we're finally going to talk about unsupervised machine learning algorithms. So again, the idea of unsupervised machine learning is that you don't have any y values available to you to make your model. So we've commonly used the example of the iris data set, and we know that it contains four attributes that are basically talking about the properties or features of a flower, and the final one is the label that tells you the species of each flower. And so what we usually do with supervised machine learning is that using those independent variables, we sort of try to predict the value of those dependent variables. But our model, if you remember, always in the fit function, if we're using the scikit-learn, will always take the x and y variables in there. So that's a supervised machine learning idea where you're telling the computer that this are the results you should be getting, so update whatever the model is doing to sort of predict these guys more. But if I were to completely remove the species column and then tell you, okay, what predictions can you make now? Then these functions, linear regression, logistic, decision trees, every machine learning algorithm we've seen so far is not going to work anymore because you're missing a very concrete parameter for those models. So in this case, you're sort of more interested in looking at the inherent features or patterns that could be hidden in your data. And so when we talk about unsupervised machine learning, the first application we think of is going to be clustering. Think of clustering as me saying that there are some hidden patterns in my data, and I'm able to point them out using some algorithms we're going to look into. So if we still go by the example of iris dataset, you'll know that if you were to plot let's say sepal width with the sepal length, you sort of see a divide between setosa, versicolor, and virginica over here. So what you are able to do is give this data to a clustering algorithm, which will be able to, without even knowing that there are species in here or multiple species, you can specify what you're looking for or how many clusters you're looking for, and it will be able to, without a y value, it'll be able to sort of say, okay, I see a cluster here and maybe a cluster here. And you could even specify, okay, what if I want you to find 3 clusters? In that case, it might do something along the lines of saying this is 1, like this is 2, and this is the 3rd one. Now, this might not be completely accurate, but that's where unsupervised machine learning really comes in, when you don't have access to this dependent variable for your data. So if you're only looking for inherent patterns and features in your data or some hidden clusters that cannot be found using supervised machine learning, that's where unsupervised machine learning really thrives and kicks in. So let's talk about our first clustering algorithm here, and it is called k-means clustering. So let's dive into what that means. Suppose I give you this scatter plot of 2 independent variables, and I ask you if you're able to find 2 different clusters in this data. And by clusters, again, I mean if you're able to sort of figure out that there are 2 different types of points here, 2 different collections. And if this was an iris data set, you could say those clusters could be the species. If this is the decision tree data set, then you could argue that the clusters could be yes, I will play tennis, or no, I won't play tennis. But right now, just by looking at this scatter plot, you're sort of able to eyeball that this might be a cluster and that might be, but that's because you are given a visual representation of the data. Now, for a computer with no visual representation given this way, we're going to employ the k-means algorithm here again. So k-means. And the way it begins, so I'm going to write these steps here and we're going to see how they affect the data. But step 0 will always be defining what the k value is. And so if I say k equals 2, so for this example, I'm going to use k equals 2, I'm asking you to find the algorithm to find 2 different clusters in this data. I could say k equals 3, and what we'll do is it'll try to find the best 3 clusters it can find in this data set. So let's go and write step 1, which will be to randomly initialize k centroids. Okay, and I'm just going to randomly initialize them first. So maybe one here, and the other one can go over here. And let's define what these centroids basically mean. So centroids, these guys, so these are centroids. Centroids are the center points of a cluster. So the idea is that you will have, once this model is finished, finding these clusters, the centroids will be the center point of each of your cluster. And we start by randomly initializing those centroids, and then what we're going to do is we're going to sort of shift them around iteratively using our steps. We're going to shift them around, and eventually what we'll hope is that they end up at the very center of what data points you think belong to a cluster. So your clusters are, I'm going to start calling them as mu1 and mu2 because k is 2 in this case. And your data points are going to be x1, x2, all the way to, let's say, xm. So these are all your data points, x. Okay, so I've randomly initialized 2 clusters here, 2 centroids for each cluster here. And the next step, step 2, is to find the distance between each point and the centroid. So each centroid and each centroid. So you can use Euclidean, Manhattan, Minkowski, it doesn't really matter. In this case, I think by default we usually use Euclidean distance, but what you're going to do is for each point, you're going to find 2 distances. So the distance from point, so this point xi, let's say, from the centroid of the first cluster, and then a distance from this point to the centroid of the second cluster. And you're going to do that for each point, because the next step is going to be assign cluster to data point based on minimum distance. So if I say that mu k are all of my centroids, so 1 and 2, and then xi is all of my data points, I'm basically looking for the minimum distance for here. So right away you'll see that if I'm looking at the distance from this point to the centroid and this point to that centroid, the minimum one is this guy. So based on this minimum distance value, I'm going to assign this point to the cluster yellow. So I'm going to say that this guy is actually yellow, and maybe this guy is a yellow, these 2 are yellows, right? And then the remaining will become green because they're closest to that centroid. So you have several greens in there. Okay. Then step 4 will be find the average of each cluster. This is the new centroid. So you can notice that, let me resize here, you'll notice that we have now sort of made a cluster that looks like this, and a cluster that sort of looks like this, right? We now have two clusters. Well, they might not be the best clusters right now, but what we're going to do is, based on these clusters that are generated by just a single first initialized step, I will find the averages, the average point for each cluster, and they will dictate what the new centroid is going to be. So for the yellow, it's sort of going to come in here maybe. And for the green, it's going to come in, I'm just going to put it here for now. So the old centroids go away, and you're left with a new centroid value, centroid for each cluster. Now after this, you're going to go back and run this step 2. So you're going to find the distance between data point and each centroid, the new centroids. Then you're going to assign the cluster to data point based on that closest centroid, and then you're going to find the averages and go on and so forth based on that. So let's look at what's going to happen visually just for a few iterations. So I've cleaned up the points a little bit, and let's go back and run step 2 all over again. So now I'm going to again find the distance between each data point and this new centroid that we've calculated based on the first iteration. And then I'm going to do step 3, where I'm going to assign a cluster to data points based on whichever's closest to them. So then we'll go ahead and we'll say that we have a, this should be a yellow, this should be a yellow, and then I'm going to say this is a yellow, and then everything else becomes a green. Okay, and that's the second iteration. And then step 4 is basically, again, finding the averages of each cluster. Now you'll notice that the clusters have shifted a little bit. And so based on that, you'll find that your clusters are going to move a little bit. This green one might move towards here maybe. Whoops. This green one might move towards here. And then the yellow might shift towards the center a little. We're going to do the steps one more time. So you're going to go ahead and find the distances. You're going to assign clusters, and you're going to then assign data points based on each cluster. So what's going to happen is that this X1 is going to keep moving in that direction a little, and it'll go here, then it'll go here, and let's say it perches over there. And the green one, based on the proximity, it's going to move somewhere over here near the end. So let me clean up these points a little bit. What I'm hoping is going to happen is at the very end, your green is going to end up over here because more points were converged for the green cluster, and the yellow one is going to come over here. Now, there is an addendum to step 4 where you check for convergence. And what that sort of means is you define a tolerance value, and you say, okay, if the new cluster, new centroid that you make after step 4 is not that far away from the previous centroid cluster, then you're going to say that I have attained convergence for my cluster. So the idea again is that the yellow one might be here, and in the next iteration it might move slightly nudge over in this direction or that direction, but it's not going to move away from this point because it's going to say that these points are now going to always be yellow. So they're never going to change to green anymore, whereas for the green, these points will always remain green. So you should be able to, after even few iterations, be able to meet a convergence point. And never have I actually used a k-means for a data set where I used more than, I'd say, at least 10 iterations for it to attain convergence. So it's very quick because you're sort of going over and looking at each data point, and based on this minimum value, these centroids move really, really quickly towards where they need to go. So at the end of your k-means, let's say for us it took let's say 5 iterations, but at the very end you will have 2 different clusters in your data, and that's the idea of what a clustering algorithm does, and that's what k-means does too. So I will add that if I were to, let's say, if I were to not have this x value and this y value, and let's put those points back in. There's a blue point here. Let's say I said that k is actually 5. Now, it's going to take a lot more iterations, I think, but you'll still end up with 5 different clusters. So let me go to orange, and let's define, maybe you might have one over here, and then you might have one cluster that looks like this. You might have a cluster that looks like this, 1, 2, 3, 4, and then maybe one like that, and the 5th one like this. So you have to be intelligent about what k value you're picking. And in this case, we sort of knew that visually the data shows 2 clusters. That's why we picked 2. But sometimes if you're looking at multidimensional data, so let's have a var3 in this case, and let's say I have a var3 in that direction, in the z-axis, then it'll be hard to sort of point out how many clusters are there exactly. So in this case, there is another method to figure out what value of k you're going to be using. But once you have found the optimal value of k, once you have defined k, these steps don't really change. So you're still going to go ahead and randomly initialize k different centroids. You're going to find the distance between every data point and each centroid. And then based on that, you're going to say that, okay, for this data point, whichever centroid was closest to it, I'm going to assign it to that specific cluster. And then you're going to find the average cluster, or the mean. That's where the name means in k-means comes from. You're going to find the average for each cluster, and whatever that point lies, that average point is going to be your new centroid. It's going to be your new mu1 and mu2. And you're going to keep doing steps 2, 3, and 4 until you hit convergence, until the old centroids don't really move that far away from the new centroids. That's when you say, okay, everything is sort of settled down, and we have the clusters we needed. One way of finding the optimal value of k is using a process called the elbow method. And the way it works is you're going to try and apply different values of k for k-means on this data, and you're going to compute the inertia, or in easy terms, the sum squared errors overall for all of those clusters for that k value, and try to plot them together. So you're basically looking for a k value that gives you a low sum squared error, right? But what's going to happen is that if I give you a k of, let's say these are 85 points. So if I give you a k value of 85, every single point is going to become its own cluster. And that will give you a sum squared error of even like a 0, but that's not a very good k value, because it's not clustering points together, it's just clustering each of them individually. So you have to be intelligent about what k value you come up with. So using the elbow method, what we're going to do is we're going to start by saying k equals 1, 2, 3, all the way to 10, let's say. And to compute the sum squared error, if this was a cluster, what you do is you find the distance. You find the distance between the centroid, this is the centroid, and every data point. You square those distances and you sum them together, and you get the sum squared error. So what we're going to do is we're going to make another plot here of k. So it's going to be 1, 2, 3, and let's say all the way to 10. We have a 4, a 5, right? And then we're going to, on this side, compute our sum squared errors. And we're going to plot those in here. So for the very first run, when k is equals to 1, this entire data set becomes part of one big cluster. And in that case, the sum squared error is going to be maximum, because maybe this is the centroid in that case, and it's gonna be very, very big. So once I do that, I will say that, let's say this is the SSE value for k equals 1. Next, we'll do it for k equals 2. In that case, you might have that you have a cluster here and a cluster there. And then for the sum squared, you're going to calculate their relative sum squared errors for each cluster. You're going to average them out. And let's say you get a value of sum squared error over here. You're always going to notice a big drop between choosing k equals 1 and k equals 2, because instead of just using one cluster, you're sort of like splitting the data into two. So there's going to always be a huge drop. Then you're going to start with k equals 3, and let's say you get one here, one cluster here, and the third one here. That's fine. In this case, again, you're going to plot the sum squared error. You're going to compute that and plug that in, and then you're going to then do it for 4. This should be the best one, and if you do that, if this was 3, 4 is going to be relatively here. So after you have found the optimal one, what is going to start happening is that your clusters, so if this was 4 and we think that's the optimal value, what's going to happen that the next ones are sort of start splitting your optimal cluster. So the 5th one might be over here. So that's now 5 clusters. So instead of these 4, you're going to end up with, let's say, 1, 2, 3, 4, 5. So it is always going to decrease your sum squared error. So it is always going to be the case that as your k increases, the sum squared error is always going to decrease, and you're going to start seeing some sort of like a smoothing mechanism where it might converge at like 0. Okay, so what we'll do now is I'm going to attempt at making a straight line between these points like this, and now your optimal point will lie at sort of like the edge of someone's elbow here. So this point over here. So the point after which the sum squared error sort of becomes really, really smooth and normalizes. So we notice here that this is a huge drop, right? This is a huge drop between sum squared error values. And if there is a huge drop over here too, there's a big one, relatively big one. There is a big one here too. But after k equals 4, things start to like really slow down in terms of the drop in sum squared errors. So we're gonna say, you have a huge drop here, a relatively smaller, and then you sort of start seeing these straight normalized lines. So we're gonna say that k equals 4 is going to be our optimal value of k, and that is what we should be using for our k-means clustering. Let's see k-means clustering in action here using the scikit-learn library, and I have loaded the iris data set here, and what we're going to do is we're going to remove the species column here and only try to use k-means clustering on petal length and petal width with a k value of 3 to see if it's still able to find the 3 species that we know exist in our data. And we're going to make a reference point here. So I'm going to say that my x is petal length, my y is petal width, and let's say the color is by species, and we're going to make a geom point. Okay, so think of this as a reference point where I'm saying that this is what the current data is, and then after we do k-means clustering, we'll try to plot what the clusters come out to be, and hopefully they'll be the same ones here. I'm really sure that the Setosa one is going to be its own cluster, but I don't know how versicolor and virginica will show up as two different clusters here. So to do that, we're gonna first set up our independent variables here, which are just going to be petal length and petal width. So to do that, I'm going to do iris.ilock all the rows, and for the columns we're going to say index 0, 1, 2, and 3, right? So we need petal length and petal width, so 2 to 4. And if I were to show you what x becomes, it's going to be just those two rows, just those two columns. Then I'm going to initialize the library or the function from scikit-learn. So from sklearn dot cluster import k-means, and then we're going to initialize a model, and we're going to say this is k-means with a number of clusters. So the k value here, this is number of clusters, is the k, is going to be 3. And I'm going to say give me a random state of 20. So if you want to run this code on your own, giving it the random state 20 shall give you the same result. So if you remember, the randomness comes in when it first initializes the 2 points, the 2 centroids, or in this case, the 3 centroids. So if you do random state 20, you're also going to have the same initial centroid points. Okay. And then we're going to do km.fit, and I'm going to pass my x value. And so it will give you some results, but to view them, we're going to say centers is equals to km.cluster underscore centers underscore. And centers will basically tell you the center or the final centroids it found for each of your clusters. So for cluster 1 that it found, this was the centroid. For cluster 2, it was this one, and then this one for cluster 3. So I'm really interested in this 1.4 and 0.24 one, because 1.4 should be here and 0.24 should be here. So it was very much able to extract Setosa as a separate cluster, which also visually also makes sense. We're also able to extract the labels that the k-means clustering will give us. So labels is basically going to be an array of 1s, 2s, and 0s, and there should be 150 of them. And what that basically means is this is cluster 1, this is cluster 2, and this is cluster 0. So I could technically go iris and make a new column. So I can make new species and give it the value of labels. Okay, and then we can go back and make our original plot again. So x is going to be petal length, y will be petal width, and color, again, let's say for now it's species plus geom underscore point. There's an error. Oh, petal length. All right, so this was the original ones. And moment of truth, let's replace that with new underscore. Let's replace species with new underscore species. And that's what we get. So let me actually pull them out side by side here. So you have one here. So let me down a little. So I don't know. Right now it looks like it was, barring a few points, it was very much able to. So this is the original. This is the original species classification for iris, so Setosa, versicolor, and virginica. And here you'll notice that I can actually, if I'm able to, I can actually make them factor, so makes things nicer. So okay, so Setosa is itself, so Setosa by itself, it makes sense. I was more interested in looking at what would happen when I modify what would happen with k-means with these versicolor and virginica ones, because there's sort of there's no boundary point here, but it seems like most of the times it did really nicely here. So one more thing I want to look at, let me go reset this. One more thing I do want to look at is what would happen if we were to change the number of clusters to, let's say, 4, right? So we're going to run these lines of code again. You're going to have 4 centroids here and 4 labels, so 1, 2, 3, and 4. And then it sort of basically broke versicolor and virginica into 2 different groups, basically. So half of it went to this new point and half of virginica went to this new point. So if you're already aware how many clusters there should be in your data, well, perhaps in that case you actually don't need to use k-means if you already know beforehand. But let's again go back and see if we're able to find what the optimal value of k would be given the iris dataset. Okay, let's design our own elbow method function here so we can use it and see what the optimal value of k should be going forward, so we're not stuck with k equals 4 for this data set. So I'm going to start by defining a dictionary SSE, so sum squared errors, and say for k in the range of, let's say, 1 to 20 even. We're going to say that km is k-means number of clusters is equals to this k value. So it's going to go from 1 through 20. And then max iter is basically you specifying how many iterations you want. Sometimes you get convergence in the first 3. And so if you're unable to find the optimal clusters, just do, let's say, 100 iterations, and after that, if you don't reach convergence, that's fine. That's the clusters you have. So what this will do is it won't do a lot more computations than it needs to. If it's already at 100 iterations and you still haven't found your your clusters haven't really converged, then in that case, might as well just move on to the next one. And then we're going to also fit our x value. Please note that x currently contains your petal length and petal width. And I'm going to then, for my dictionary, I'm going to add a key k, and I'm going to say this is equals to my model dot inertia. Inertia here is what I was describing as the variance of your data. So this is going to be the sum squared error of all data points within a cluster. And it will sort of give you a nice idea of how well your clusters are defined. So I'm going to do that, and just to show you what's going to happen, these are all the 10 clusters that ran really quickly. And so for every k value, you've made one cluster, you found your inertia to be 550, and then for 2 clusters, 86, then for 3, 31, and so on and so forth. Then you'll notice that it keeps going down as you go. So what we're going to do is we're going to plot this out. So before we do, we need to convert it into a data frame to give it to the ggplot function. And I'm going to say that I have a variable called k colon, and because SSE is a dictionary, I'm able to say give me the SSE dot keys. So the keys should be all the k values here. And then I'm also going to say that I need the SSE, which should be, again, the list of the values from my dictionary. And now I can do ggplot. The data is going to be df. And my aesthetics, x is going to be k. Y is going to be SSE. And I'm going to have a geom line function here. So that's what you sort of get. So again, as k increases, you're sort of getting closer and closer to that 0 over there, but that's not what we care about, because that's not a higher value of k. Well, it will always mean a lower inertia, a lower sum squared error, but that does not mean that we're doing smart things. So instead, we're going to use the elbow method. And the way, again, you look at things to find which is the optimal value here is you're sort of going to say, okay, there is a huge drop. So I can assure you that this is 4, this is 3, here you have 4, 3, 2, and 1. So you'll notice a huge drop in SSE from 1 cluster to 2. That's great. And then another significant drop between clusters, k equals 2 and k equals 3. And then you're going to sort of see like a smooth convergence going down. So in that case, which one do you pick? Do you pick k equals 2 because it noticed the biggest drop, or do you pick k equals 3, after which there is a streamlined process? So using the elbow method, we're always going to pick this guy, after which there is a normalization, a sort of like a smooth line going on, because what's happening here is that between 1 and 2, there's always going to be a huge difference. You're saying that you want a cluster on your entire data, k equals 1. And then you're saying, okay, make that 2. So this is always going to be a huge drop. But what you're more interested in, what happens in the what happens after k equals 2. So notice here that there is still a significant drop in SSE here. There's another one at 4, but it's not that much. It's almost as if it's matching the 5 afterwards. So in this case, we're going to pick k equals 3 here as our optimal k value, and that makes sense because in this Iris dataset, you do have, in fact, 3 different clusters going on. One final word on k-means clustering is that it's a pretty easy algorithm to implement, and we might be actually doing that for our next assignment, but be mindful of the fact that it won't be applicable everywhere. And by that I mean that if you were to sort of say that I have variables a and b, and this is what the plot is like, a very dense region of plots, well, no k value is going to give you a good clustering in this case. It'll just say that you have one giant cluster going on in here. So even with this case, even with the case of spherical data, so think of this thing, and maybe I have another cluster in the middle like this, and then there are a couple of examples. These are very cool data sets that have these data points like this. And so in this case, the k-means algorithm won't be able to discern that there is some sort of a spherical cluster over here, or some sort of a curved cluster over here, or that inner circle in that case. So it might not do well where a specific cluster is very distinctly available or very distinctly visualizable in your cases, but it is very easy to implement, and it's sort of going to lay the groundwork for more upcoming unsupervised machine learning algorithms.